So up to this point, we have only been applying the derivative to a function once, but there is nothing in the definition to uh, inhibit us from taking the derivative as many times as we want to. And in fact, there are many instances where second derivative, third derivatives have interpretive meaning. For instance, acceleration is the rate of change of velocity. Well, velocity is the rate of change of the position. So then acceleration, you would compute it by taking the derivative twice of your position function. So let's establish what we mean by a second derivative and the notation we'll use. So a second derivative is the derivative of f, and we denote it with the, if we're using prime notation, we denote it with the double prime notation as we see here. So we got f double prime. Now, the third derivative of f is the derivative of the second derivative, and we will denote that with a triple prime, or sometimes to make it easier to read, we'll raise it to the 3, but we're sure to put parentheses in here because we don't want to be mistaken of this to mean the function raised to the third power. So when we put parentheses, we're saying, hey, we're going to do the derivative 3 times, and in general, the nth derivative is the derivative of the n minus 1 derivative, and we denote it again as f raised to the parentheses n. That's our notation. We'll never say parentheses raised to the parentheses n. We'll just say the nth derivative of f. So how does that pan out in regards to differentials? Well, if y equals x and f of x, y equals f of x, sorry, then the second differential of y, and we'll denote it as d raised to the 2y is equal to f double prime of x dx squared. And in general, the nth differential, dny, is the nth derivative of f times dx to the n. And this gives some nice notation, comparing the Leibniz notation to the Newtonian notation, that if I talk about the second derivative of f, I could write it this way, d squared y over dx squared. And when I talk about the nth derivative, I can denote it by dny over dx to the n. So let's give some justification. It's not going to be a proof by any means, but a justification of this notation here. So let's just start with what would be the second differential of y. So y is equal to f of x. Then we know that dy, by definition, is the derivative of f dx. And so the differential of the differential of y would be the differential of f prime of x dx. And we will, technically not true, but remember this differential dx is oftentimes associated with the infinitesimal, so we can think of it like a constant. So when I take the differential here, this dx is a constant. And then on the left-hand side, instead of writing this bulky thing, I've got a d and a d, and so I'll rewrite it using squared notation, which makes you think, oh, I'm applying the differential twice. So on the left, this we write d squared y. And on the left, well, the differential of f prime is the derivative of f prime. So this would be f double prime of x dx. So that's what the differential of f prime is. This is just the differential of this piece, right? Because it's a differential. So we get the derivative of the function times dx. But don't forget, we've got this other dx here, and so we need to write it, bring it back down. And so this whole thing is times dx. but this is dx times dx, and so it's f double prime of x dx squared. Similarly, if we wanted to kind of continue this out, d cubed y is the differential of the second differential of y, which would be the differential of f double prime of x dx squared. And again, following what we did in the last step, this would simply be the triple derivative of x dx times our leftover dx squared, which would be f triple derivative dx cubed. And we'll use this kind of reasoning to compute plenty of other derivatives if we need to compute higher order derivatives using the differential forms. So as I said in the intro, we know that acceleration is the rate of change of velocity. So acceleration, we'll denote it by, say, a is equal to the rate of change of velocity. But if, say, velocity, it's a derivative, we know it's the rate of change of our position function. So that means putting these two together, right, combining these two ideas, that acceleration is the derivative with respect to t of velocity, which is the derivative of position with respect to t, which is the second derivative of position with respect to t squared. So right off the bat, we know that acceleration, if we've got a position function, then acceleration is simply the second derivative of that position function. So let's look at, let's compute an example. So let's set y be equal to e to the x squared. And I'm going to want to know what is the second derivative of y with respect to x. So to compute the second derivative, we're going to have to compute the first derivative first. So, and we'll do this all in differential form. So dy is equal to the differential of ex squared. And just so we're remembering our differential rules, so the differential of e to the u is equal to e to the u du. So we can move forward. Our u is x squared, so this is going to be equal to e to the x squared dx squared. And now this is a power rule, and so the power comes down when we take the differential. It'll become the coefficient, and this power will go down by 1. That's our power rule. So this is equal to ex squared times 2x dx, or more naturally, 2x e to the x squared dx. Okay, that's what the differential of y is. So what is the second differential of y? Well, the second differential of y is just the differential of the differential of y, which we calculated in the previous step. So this is the differential of 2x e to the x squared dx. And now I've got a product rule, right? I didn't originally, but now after taking the derivative once, I've got the product rule, right? I've got 2x times ex squared. Remember this differential dx we treat like a constant. So this is equal to, using the product rule, is equal to the differential of 2x times e to the x squared plus 2x times the differential of e to the x squared all times dx, right? This constant dx was able to come out like it does with differentials. And so now this is equal to, so the derivative of 2x is just 2. So this is 2e to the x squared dx plus 2x times, and we don't have to compute this differential again because that's what we just did in the previous step, right? The differential of e to the x squared is simply 2x e to the x dx. So I could just put that here. This is 2x e to the x squared dx all times dx. And now I'll clean this up, and so this is equal to 2e to the x squared plus 4x squared e to the x squared quantity times, now that dx and that dx comes out and multiplies by that, so it's dx squared. So putting this all together, we get that the differential of e to the x squared dx, which was our y, so we divide this whole thing by dx squared, is simply 2e to the x squared plus 4x squared e to the x squared. So that's the differential of e, or this bad notation. I didn't want to know that, right? Notation-wise, squared. Thank you for catching up. Okay, so that's the second derivative of e to the x squared.